continue, I just want to make some remark that in this definition, as you see, I mean, to give such a definition, you need to really, I mean, you need to know what you are doing, because I mean, it's not a kind of definition which you encounter, I mean, in the natural way. But what I want to explain is that this notion of nuclearity, just the category of nuclear model, can be obtained by trying to answer some very naive questions of general categorical nature. So that's roughly what I'm going to explain. Now I will express this solid modules in terms of this perfect complexes with torsion homology. So we take again the generator and take its DG algebra of endomorphism as a proper DG algebra over R. So modules are identified with derived category of R modules with torsion homology. And so one can make the following observations. So first, when we take compact objects in this derived category of solid modules, then one can show that this is simply the opposite category to the category of bounded complexes of projective R modules with I-torsion homology. And this anti-equivalence sends this product of copies of completion of R to the direct sum of just local homology of R of S. And checking that this is indeed anti-equivalence is really an exercise. It's not very complicated. And in particular, these compact objects also.
I'm sorry.
Yes.
I had a connection problem. So I was unable to. I was disconnected. So can you say again what's going on?
Yeah, I was making a remark that I will explain that how do you obtain this such complicated notion by trying to answer very naive categorical questions.
Good. And now you're going to reformulate the same object in more understandable terms.
Yeah. Yes. It's definitely more understandable to me, but I think probably for everyone. Yeah. So the observation that which I made, that this compact objects in this solid modules, this is just the opposite category to bounded complexes of projective R modules with I-torsion cohomology. And the anti-equivalence sends the product to the direct sum of copies of local homology of R. So this is basically an exercise, and the tensor product under this anti-equivalence, it corresponds to the usual tensor product. I mean, of course, derived tensor product over R.
Again, I want to understand the baby case. Suppose that suppose R equals CP, I
yes.
is generated by P.
Generated by P, yes.
Then what are you doing?
Then basically here you get the copies of QP mod ZP.
So what do we take
shifted
as
by -1.
Can you explain slowly what happens in this case?
Yeah, in this case, you have so this anti-equivalence sends the product of copies of ZP.
First of all, who is so R is
ZP. But
R is the I forgot the notation. Is R the Cauchy is an ideal in what?
No, I don't require R to be complete. So R is some Noetherian commutative ring, and I is ideal. So in this case, particular case
R is D. R is D, and I is generated by P.
Yes, but
yes,
you also get the same. Yeah, I mean, you also get the same category if R equals Z and I is generated by P.
And then you just consider the bounded derived category of P-torsion groups. Just a moment. So complexes are bounded, but does QP mod CP live in this category? So do you require? What does I-torsion mean? Does it mean that?
Yes, I mean, yes, I mean that a module is I-torsion if each element is killed by a power of I.
But this power, there is
this
no
power
bounded,
may be unbounded.
In this yes. So, for instance, QP mod CP lives inside your category.
Yes.
Good.
Yeah, but projective models are projective models are infinitely generated here. Yeah.
Yes, infinitely generated.
Maybe our tors. What does proj R mean here?
Just infinitely generated projective models.
In over what ring or
over R? I mean, in this particular case, you can consider R equals ZP, or you consider R equals Z. And the result.
When you write I-tors, does this mean that the cohomologies are?
Cohomologies, yes, cohomologies.
So you consider bounded complexes of free abelian groups whose cohomologies are P-torsion, but there is no boundedness condition for the powers of P.
Yes.
That occur. So, for instance, QP mod CP lives in this category.
Yes.
And
yes.
then. Okay, and then this is the right-hand side, and now the left-hand side contains the letter omega, I believe. What is the meaning of this letter?
No, it's just notation for compact objects. I mean.
I see. So now you consider the now this category is the category of compact objects of a certain compactly generated category. Yes. And this bigger category, or another name for this would be the category of int objects of the previous category. And then this category of int objects is what you want. Yes?
Yes.
Also, Volodya, sorry to interrupt, you said that you replace projective models by free modules, and for integers, whether any projective modulus is free, it's independent on
Maxim, it's true. No, it's true. There is another problem which is independent of ZC. It's Whitehead. It's about X1 to Z. But that projective are free. This is well known.
No, of course, projective and free are the same in this baby case. Yes.
Sorry, Sasha, can I ask a question? In what sense do you take a derived category of this bounded complex of projective modules with I-torsion homology? I mean, if you take bounded complex of projective modules, doesn't it already kill the quasi-isomorphism?
Of course, it's the same as homotopy category of.
Just homotopy category, sure.
Yeah.
No, probably not homotopy category, but DG category.
No, I mean, Timothy was asking about the difference of derived categories and homotopy categories of abelian category. I mean, on the level of triangulated categories, it's just maps of complexes up to homotopy. That's what we meant. Yeah, but of course, I'm considering DG categories. So, yeah. Here, I'm considering just home complexes between complexes of projectives. Yeah. So in the example which Vladimir mentioned, ZP when let's say R is Z or ZP and I is generated by P. In this case, this anti-equivalence is well, at least for the faithfulness of this functor is basically Pendragon duality applied to pro-P groups and P torsion groups. So this is quite standard, but I mean the same holds in this more general setup, and it's not really hard to check. And not only for the faithfulness, but also that this is actually the same category. Okay, so and the solid tensor product on this category of compact objects corresponds under this anti-equivalence to the usual tensor product over R on this category, bounded category of projective models with torsion homology. In particular, so tautological observation that we can also define this derived category of solid models as the category of left modules over the DG category of bounded complexes of projectives with I torsion homology. And we now want to interpret the notion of nuclearity in terms of the DG algebra A. So I will give the answer, but I mean, to figure out that this answer indeed describes nuclear models, it's some kind of direct computation, which I will leave to the interested listeners. Let's define mod BA as a full subcategory of A models whose underlying complex of R models is quasi-isomorphic to a bounded complex of projectives. Then this mod BA is just the same as the category which I considered above. And again, it's anti-equivalent to the compact objects of solid models. Also, let's define the full subcategory of the Kalkin category to be formed by, well, let's say direct summons of the images of bounded complexes of projectives, of projective R models. And then it turns out, surprisingly, that and this is less trivial than 1 and 2, which I mentioned above, but it is essentially obtained by unraveling the definitions and unraveling the equivalences of categories which participate in this picture. That a left module M over this DG category of mod BA, it corresponds to a nuclear module over the completion if and only if it is contained in the kernel of left modules over this bounded category of A modules to models over left models over representations of A opposite in the Kalkin, in the bounded Kalkin category. It's not actually immediately obvious that it is the same as the definition which I mentioned earlier, but it's really what you get when you unravel the definition and try to express everything categorically.
Sasha, yeah, I have a question. Yeah, you have bounded, yeah?
Yes.
Yeah, it's kind of bounded in a homological direction, but projective of arbitrary rank. Yeah, so it's kind of bizarre combination of bounded and unbounded. Yeah.
Yes, it looks strange because I mean it makes sense in general to consider either bounded categories of some small modules like coherent or perfect, or you take unbounded category of large modules. But here somehow they Clausen and Scholze they consider such intermediate objects like bounded category of large modules, and in this condensed formalism is really important in some cases because in this case, the notion of pseudo-coherence becomes important. I mean, a lot of technical results are proved by noting that something is pseudo-coherent. So this pseudo-coherence makes sense when you consider such intermediate objects. If you would consider just for the compact objects, you will take unbounded category, then pseudo-coherent objects, they don't make sense. You have compact or non-compact. There's nothing intermediate. So it's some non-trivial.
So for example, for Z-mod 2 graded categories, you don't have such.
Yeah, for Z-mod 2 grades, you don't have such.
I see.
Yeah. Okay, so yeah, so this is not obvious, but this is basically unraveling the definition, and this categories and this functor, they make sense, as I mentioned, for an arbitrary property algebra over the base commutative ring, and so we're approaching to we're approaching the general definition, and a very surprising fact which I discovered while thinking about this. This proposition motivates the following general construction. We take a property algebra over a commutative ring, and we define the following DG category. Yeah, here I drop the bounded assumptions because I have to do it if I want to work with abstract property algebras. I mean, this bounded versions, they don't really work well for abstract property algebras. So here I'm doing a very naive thing. So I'm taking modules over modules and modules over representations of A opposite in the Kalkin category. And take the kernel. Okay, this looks like some strange definition, but there is the following very surprising result, that this functor from A modules to representations of A opposite in the Kalkin category is a homological epimorphism. Yeah, and when I was thinking about such constructions some time ago, like 5 years ago, I think, I didn't even consider such possibility because I thought that it just doesn't make sense at all. But it turns out that this is indeed the case, and this is the case for an arbitrary property algebra. And the second statement is that, which is again up to set theory, this is immediate corollary of the first, that this general category of nuclear modules is dualizable presentable. Yeah, there's some notational problem here. I should probably use some different notation like nuclear tilde or something to stress that I'm considering unbounded categories. So it's in this geometric setup, this is some enlargement of the category of nuclear modules, which Clausen and Scholze consider. But on the other hand, this category will give an answer to some general abstract question. It satisfies some universal property inside the dualizable world. Are there any questions here at this point?
Sasha, may I ask a quick question? This homological epimorphism, is it just, yeah, could you remind, it's just the same as saying that there's a fully faithful right adjoint, which maybe...
Yeah, when you consider modules of these categories, then the right adjoint is fully faithful. Yeah, I mean, restriction of scalar. It's also the same if you are more familiar with, I don't know, homology epimorphism, it is the same thing.
Okay, but does it also say that the right adjoint is continuous, or this is not true?
No, for this category, there is no right adjoint. The right adjoint will appear when you take modules over these categories.
Yeah, but I mean, this
will be fully faithful.
Okay, but okay, thanks.
Mm-hmm.
Sasha,
Yes.
may ask, so suppose your A is some exterior algebra in one variable or maybe in several variables. Is there a way to describe this nuclear category in terms of polynomials in some way so that we would feel the geometric nature of it or whatever?
Well, it's possible, but
so there's no direct way?
It's not a way which can be described in 2 words. But roughly, roughly in this, let's say we consider QP, which is not really a formal scheme, but just still to give an idea. Then in this functional analysis, there is notion of Smith spaces, and there's duality between Smith spaces and Banach spaces. And in this particular case, the generating collection of objects is given, but by what you can consider as Banach spaces over QP. But I will probably not go into detail here because to really explain what's going on, it would require some additional explanations.
Okay.
Sasha?
Yes.
So you formulate this definition for any proper DG algebra, and then we have to believe you that this is a reasonable notion. Now, what are the typical examples of proper DG algebras that I have to keep in mind?
Well, no, I think that the basic examples are really coming from algebraic geometry. I mean, from this perfect complexes with support. But you can also keep in mind a trivial case, which I will mention it actually on the next page, that when A is smooth and proper, then this is just the usual A-modules. I will comment on this.
But the interesting case is when A is proper but not the more.
Yes, the interesting case is
when A is proper but not smooth.
Yes.
And here the main example is, for instance, what are the main examples? For instance, you can consider the category of the DG category of perfect complexes on a proper singular variety.
Yes, that's already an interesting example, and it's
and
not.
So, okay, if it's interesting, then maybe you can say something of why it is interesting. For instance, why are nuclear modules in this case useful for humanity?
First, I will comment on the case of singular scheme. Let's say proper singular scheme over some field. Then this compact objects in this category, these are just direct category of quasi-coherent shapes. And kind of philosophical remark is that you can think of coherent shapes as kind of Cauchy dual to perfect complexes in this case. But what I want to claim somehow is that the real Cauchy dual object is actually this category. I will probably explain what I mean later,
okay, so just a moment. By the way, Dennis Gates-Goria introduced a certain category which he calls the category of incoherent sheaves.
Yes.
Is it somehow related to?
It is contained as a full subcategory inside this category, because I mean, when you have dualizable category and you have, if you know the compact objects in this category, then int objects of these compact objects, they're contained inside the dualizable category.
Okay, so are you saying that your category of nuclear sheaves is a full subcategory of the category?
No, it's bigger. It's bigger than incoherent.
It's bigger than incoherent.
Yes.
But still useful.
Yes, from some point of view, yeah.
From some point of
And
Yeah.
maybe one question, suppose you have just a point on a line, yeah, and get exterior algebra in one variable, your algebra, mod of S1. So it should be some kind of like vector spaces with some operators, endomorphism.
Yes, I think in this case, this category, yes, I'm not ready to give some presentation of this category in terms of some small collection. I mean, in terms of some small data, but I think it can be done. So, I mean, this is actually abstract definition, and I think that in some cases these categories can be really expressed in much more comprehensible terms. For example, as kernels of some localizations, but between something small, like visible algebras. But I'm not ready to discuss this in detail. So, so far, I mean, I've discovered this like a couple of weeks ago. So I was thinking about rather some general questions here. And I wasn't actually believing that this statement is true, so I was checking it several times that the proof is correct. So, so for now, let's focus just on this abstract statement, and then we can also discuss what happens in examples.
Sorry, could I just ask a question about the abstract statement?
Yes.
So sorry, so here you're considering A modules in K modules and A modules in the Calkin category, as I understand.
Yes.
And the functor from all modules to the Calkin category is a homological epimorphism.
Yes.
But I guess I would imagine it's not in general true that if you have a homological epimorphism and you take A modules, it remains a homological epimorphism.
Yeah, it's not true at all. Yeah.
Huh, I see. So
And
it's something special.
That's why I wasn't believing that this statement. So yeah, but I will try to explain why this actually works and what is the relevant computation, which is quite non-trivial, and what is the universal property of this category. So why it gives an answer to some naive question. Okay, so I will sketch the proof and explain the universal property and also actual generalization of this category. It's a special case of even more general construction. First, we make the following observations. If A is smooth and proper, then as I already mentioned, this category is just A modules. And this is because basically because A, well, more precisely, perfect complexes of A are dualizable in just small DG categories. This allows to rewrite such constructions. So representation in the Calkin category is the same as Calkin category of A. And then tautologically for any DG algebra or DG category, we have a short exact sequence models over B to models over B to models over Calkin category over B. This is just because we have localization on the level of compact objects. So this is the kind of simple, very simple special case. And if A is proper, then as I probably already mentioned, assuming the theorem, we immediately have that the compact objects of this nuclear category is given by pseudo-perfect A modules. And this is just the kernel of the functor between these categories.
What is a pseudo-perfect?
The modules which are perfect over the base ring.
Ah.
Yeah. So this is more tautological, actually, just the kernel of this functor in part 1. Okay. So now I will sketch the proof. So at least how is it possible to make such computations? So for an A module, we have two kinds of dualities. We can take dual over A and dual over K. So I'm writing M star for the dual over the base ring. So the crucial point is to prove that this functor is homological epimorphism onto its image. So as I mentioned, this already implies, of course, dualizability. And this is really the main statement here. So this translates into the following. So you take any two modules over A, and you need to check that the natural map of some natural map is an isomorphism. Now, what happens here is so these guys, they are modules over this category of modules. So in other words, this right module here is a contravariant functor, and left module here is a covariant functor. So these functors are given, for example, the right module is given by the following. You take any A module, you take its dual over K, you tensor it with N, tensor I mean over K. And then you take Hochschild cochains of A with coefficients in this product, and similarly here. So now this maps, and this is very weird tensor product. So we just ignore the fact that mod A has infinite direct sums and consider it just as an abstract DG category. Well, ignoring set theory once again.
Can you just replace it with the matrix algebra of large size?
Yeah, but the problem is, again, you can bound everything to deal with.
So you bound and then
small categories.
One single matrix algebra of large size, and that's enough, right?
Matrix algebra of large size, well, not really, because when you take some fixed object, then the category generated by it, I don't think that it's sufficient for such computations.
Okay.
I'd rather say that you take a couple small modules for some large cardinal kappa.
Okay.
Yes. Okay. So this is basically, as I mentioned, the homological epimorphism is a statement about some tensor product over the source, and here the source is mod A. So here you need to show that such tensor product is an isomorphism. Now we can replace this M star with some left A model P. So we have the same question, but just P instead of M star. We just forget the fact that M star is dual to something. So we want to prove that such map is an isomorphism. And this looks a little bit surrealistic because it looks just totally impossible to compute such tensor products, because both modules are very far from being representable, and it's not clear how to compute this at all. But so it turns out that you need to carefully deal with the interaction of limits and colimits here, sequential limits and filtered colimits. So I will briefly explain what's going on. So first, recall this UP6 axiom of Grothendieck, which is satisfied for abelian groups by a direct computation. So this UP6 is the following, that for any small set and any collection of filtered categories indexed by this set. So we have ij is a filtered category corresponding to j. So if we consider a collection of functors from each ij to abelian groups, then you have the following fact, that the product of this filtered colimits can be expressed as a filtered colimit over the product of ij's of products of mij. So it's really just an exercise on this, how these filtered colimits, how you construct them in abelian groups. So you just check this element-wise. Just looking at the element on the source and the target, and just checking that this is a bijection. So this is easier, and since products and filtered colimits are exact in abelian groups, the homotopy version of this also holds in derived category of abelian groups and in spectra, and in particular in any compactly generated category. I don't think it holds in dualizable categories. At least it's not obvious. but it holds in any compactly generated category. Okay, now to compute the tensor product, so I'll just explain how this is done. Let's represent our DG algebra as a sequential limit of smooth DG algebras. So limit of B1, B2, B3, and so on. And it's more or less obvious that this can be done. It can be done actually for any DG algebra whose underlying complex is Aleph1 compact. I mean, just countably generated semi-free K model. And let us represent the left A model. So once again, we have the left A model P and right model N. So let's represent this left model as a directed colimit of perfect. So some directed poset I. And consider this positive integers as a partially ordered set with the usual order. And then we have the following chain of isomorphism of left models over this huge DG category mod A. And yeah, it might look scary, but I'll just briefly comment on what's going on. First, Hochschild chains of A with coefficients in something is the same as limit of Hochschild chains of Bn with coefficients in the same bimodal, over A. Now, this I expressed P as a directed colimit, and using the fact that Bn is smooth, it follows that Hochschild chains of Bn they commute with filtered colimits. So I can write it as sequential limit of directed colimits of Hochschild chains. Now this is you immediately observe that this is the same as limit of colimits of R homes from Pi star to something, and then you employ this UP6 axiom together with the telescope construction, which allows you to compute sequential limits, and you get this expression that this is the same as limit over all maps from positive integers to I of inverse limit of such R homes, where the inverse limit over well, n less or equal to m. Here, this guy is it's contravariant in n and covariant in m. Yeah, so this is basically by obtained by using this UP6 and the telescope construction for the sequential limit. And then tautologically you obtain that you express the model from which we started with as a colimit, actually directed colimit, because this maps from positive integers to I, they form a directed poset themselves of R homes from some model. So in other words, we represented our left model over the category of models as a sequential, I'm sorry, as a directed colimit of representable models. And this is already quite nice because we can use this to compute tensor product, because it's easy to compute the tensor product of a representable model with anything. It doesn't matter over which category you compute it, because it's representable. So in particular, it doesn't matter which size, this huge size of mod A, it's irrelevant when you're reduced to such representable models. So that's the first observation. And here it's really important that I have a countable limit, because otherwise it will be hopeless, I think. So once again, we applied here the smoothness of Bn, axiom UP6 together with the telescope construction to write the limit of colimits. So and then using this computation, I mean partial computation, you can express the tensor product quite explicitly. Well, as explicit as it is possible to do for such computations. We also represent the n as a directed colimit of perfect modules. Then again, by applying the previous computations and by again playing with limits of colimits, we are reduced to the following: that we take so to compute this tensor product, we take a limit over all pairs of maps, directed limit over all pairs of maps from positive integers to I, and another map from positive integers to J, and then inverse limit over n less or equal to m and k less or equal to L, R home over Bn opposite tensor Bk from A to this product of perfect modules. Now, then you want to compare it to actually to Hochschild chains of A with coefficients in P tensor n, and they can be written as a limit, inverse limit of colimit over I cross J of R home over Bn opposite tensor Bn from A again to this products of compact approximations of P and N. And then all you need is just one more observation, essentially, that if you consider this functor two copies of positive integers cross I cross J to complexes of abelian groups, then it satisfies the following conditions: that if you fix K, then the limit just commutes with, you can just replace, you can take first the limit over n of directed colimit over I cross J, or first, or the other way around. So it basically follows directly from the definition here. Similarly for n. And then, yeah, this is, I think, I'm sorry, this is, I think, impossible to follow, but I just want to give the conclusion that under this assumptions on this functor, you have a certain general assertion about this interaction of limits and colimits. Yeah, so it's not an everyday computation. Yeah, and I was checking it several times, and now I'm quite convinced that it works. And so it finishes the proof that of the fact that this functor is a homological epimorphism onto its image. And I guess this proof simplifies considerably if you consider only bounded models, which is a situation which is considered by Clausen and Scholze, because then you essentially you don't need to consider arbitrary directed colimits. You just need to consider infinite direct sums, and then yeah, then this computation simplifies, but it's still not an easy statement. Okay, so yeah, this was the scary part. So the conclusion is that this category of nuclear models is dualizable presentable up to set theoretic issues, but there is stabilization when you enlarge the regular cardinal. So now I want to give an alternative characterization of this dualizable category by universal property and formulate a more general statement. Are there any questions? Or any doubts, for example, that such computation might work?
You see, I think Volodya already left, so there's questions.
No,
Okay.
but that's what I told you, Sasha, that I looked at the slides and it's impossible to follow if you see them first time.
I believe it, for example, no problem with me.
Okay.
You believe? You believe.
Yeah,
Who believes?
Galidin.
Yes,
Okay,
I mean,
okay. Okay.
I can't
yes.
say details, but
Second, it's not a matter of belief. Yeah, so.
Yeah, okay. So now I want to give an alternative characterization of this category. So recall that this digicut dual was an infinity category whose objects are presentable. I'm sorry, dualizable presentable. Yeah, here it's missing. Dualizable presentable digicategories, and the morphism are given by strongly continuous functors. Then it still has the same symmetric monoidal structure given by the Lurie tensor product, because tensor product of two dualizable categories is again dualizable. And now we can ask the naive question. So in this category, in this symmetric monoidal category, given two dualizable categories, does internal home from C to D exist? And if yes, can it be described in some explicit terms? In general, it seems that the answer is no, at least if you care about such theoretic issues. So the point is that if you fix some infinite regular cardinal and restrict to K-presentable dualizable categories, then this existence can be proved by abstract reasoning, but it seems impossible to describe it explicitly. I mean, it can be, of course, described in a special case when this cardinal is omega, in which case we just consider completely generated categories, and this internal home is given by models over functors between compact objects. But in general, I mean, it's something totally incomprehensible, and there is no stabilization when you enlarge cardinal.
So it's omega has two meanings here, because you have omega upper index mean compact objects.
No, it's the same, yeah, but no, omega small. I mean, omega is the same as aleph 0.
Aleph 0 it's countable, yeah, but
yes.
but compact objects, it's not related to the notion of countable, because
no, but it's less than countable. I mean, any
less than
any motion to there are some factors through less than countable sum, which means finite.
No, but you do not, before C with upper index omega is, you do not, it's like compact objects.
It's a clash of notations.
Clash of notations, yeah. I think you do not compact.
No, it's the same. I mean, omega compact is the same as compact in the usual sense.
I see.
Oh.
Okay, good to know.
Just by definition.
Okay.
So let's denote this internal home by home underlined dual. So we have the following result that I still do not believe it. I mean, this statements, but I think I'm convinced now. When we have a property J algebra over K, then this internal home dualizable categories from models over A to models over K, it exists, and this is just the category of nuclear models over A opposite.
For any sufficiently large cardinal, right? Or just in general?
No, here it's not about cardinals. I mean, this symmetric monoidal category is defined regardless of cardinals. So in particular, we have stabilization.
Okay. Okay. Yeah. So it makes sense. Yeah. Okay. Right.
Yep. Now, moreover, for any small digit category T, if you consider this functor from bimodals to representations of A in Kalkin category of T, then it is a homological epimorphism. And moreover, we have that this internal home is given by the kernel, the same kernel as above, but here we have models over bimodals to models over representations of A in Kalkin category of T. So this really computes the internal home in dualizable categories. And for a short exact sequence of small triangulated categories, we have a short exact sequence in dualizable categories. which was again quite surprising for me, because you get nothing of the sort for usual functors of small categories. As Achille actually asked already, that I mean, there's no like projectivity property for usual functors from A to something, but in this context, it turns out that their models over A are projective with respect to internal home in dualizable categories, which is kind of insane if you think about it. But this in particular explains the Zariski descent for K-theory, continuous K-theory for nuclear models. Just is basically a special case. Yeah, but still the statement is much more general. And here I didn't include it, but here you can even consider, instead of models over T, you can consider some dualizable category and again define, give the same definition, and again everything works. Yeah, so in particular, applying any invariant to home dual from mod A to something, you get a localizing invariant. Of course, the question is it manageable? I mean, is it even possible to compute such invariants? And this I cannot answer at the moment. But at least you have this general picture. Yeah. So in particular, just to stress that in the case of formal schemes, when you consider this Clausen and Scholze construction, it gives a full subcategory of this internal home and full subcategory with continuous right adjoint. Okay, so this is basically the interpretation of this nuclear models in terms of universal properties. And we briefly explain why the condition 1 holds, ignoring set theory once again. And part 2 is straightforward generalization, and part 3 is obtained quite formally. You need to be careful, of course, with such statements, but it is quite formal. So the argument for part 1 is the following. You have some non-standard adjunction here. If C is dualizable presentable and D is presentable, then strongly continuous functor from C to modulus over D is the same as continuous functor from C to D. And in particular, this allows you to express strongly continuous functors from C to modulus over left modulus as continuous functors from C tensor mod A to mod K. And then you just, you need to figure out for a continuous functor from C to A modulus. What does it mean that it corresponds to a strongly continuous functor from C to nuclear modulus? So that this strongly continuous functor from C to modulus over modulus factors through nuclear modulus. And this is actually the condition that the composition C to A modulus to representation of A in Calkin category factors through Calkin category of C. This can be checked directly. And the same condition characterizes continuous functors from C to A modulus such that the associated functor is strongly continuous. Yeah, I mean, you really need to check here what's going on, but that's how it works. So this shows this assertion that nuclear models over A opposite they're given by internal home. Now, computing invariance again, it's not easy at all here, but at least there are some reasonable expectations here. So it can be deduced formally that from the construction, well, similarly to the assertion about pseudo-perfect models, that the Hochschild homology of this dualizable category is the same as Hochschild homology of A. It's again some kind of renormalization, but in this dualizable framework. More generally, we have the same statement for internal home dualizable categories. that this is the same Hochschild homology of A opposite tensor T. Now for Hochschild homology, I don't really know how to do this, how to make this work, but it seems plausible that this Hochschild homology of this nuclear category is just a dual K model to Hochschild homology of A opposite. I guess this is what Dima Kalizan asked me some time ago for pseudo-perfect, but for pseudo-perfect models, it fails for stupid reasons. But here it seems like this might work. I'm not completely sure about this, but one need to understand better how to express this category of nuclear models.
So basically,
I don't understand this at the moment.
Something, right?
Once again?
Basically, the hope is that this gives you formal power series as Hochschild homology.
Yeah. Well, dual space, yeah.
Mm-hmm.
Yeah.
Do you
mean for formal schemes? Yeah.
Like pointed line. Yeah, I mean, some trivial example.
Do you have to kind of, we'll have to check it separately, like for different versions of homology theories, like for Hochschild homology, it's okay. For Hochschild homology, you're not sure. For periodic.
No, but I mean for periodic. No, I mean the main statement I think is for Hochschild homology, because, well, for periodic you need to be careful because this product. But I think I mean the basic statement is just for Hochschild homology. If you know this, then you know this, for example, for cyclic homology. I mean, not negative cyclic, but just cyclic. But you need to be careful with negative cyclic and periodic. Okay, and for continuous K-theory, I expect that if I express A as a sequential colimit of homotopically finite the J-algebras, then this continuous K-theory of nuclear models is the inverse limit of the usual K-theory of pseudo-perfect models over Bn. So this is some kind of analog of the statement which is expected for formal schemes. And again, to figure out whether this holds, one needs to understand better how to construct, how to approach this nuclear categories, so how to express them in some reasonable way. So I don't have a clear understanding of this whole picture at the moment, but it seems like this might work. Finally, I will mention something completely insane, but this is just concluding remarks. What happens when you think about neighborhood of infinity? So when you take homotopically finite J-algebra, let's say over a field, and you want to understand this nuclear category of punctured neighborhood of infinity, which in the algebraic geometric situation gives the category of nuclear models on the formal punctured neighborhood of infinity. So you can compactify, and then you cut out the infinity locus, and the result doesn't depend on the compactification. So there's a well-defined adic space at infinity.
Is this thing proper?
Once again?
Is it proper? I mean, you need it.
Proper.
B
is not proper. It's just finite.
B-hat infinity.
Once again.
B-hat infinity. I mean.
No. It's just notation. I'm sorry. It might be confusing. It's just notation. So consider this symbol just as nuclear. Okay. So some category associated with neighborhood of infinity. There's no immediate meaning of this B-hat infinity.
Okay.
So first, recall some construction which I observed several years ago, that the usual perfect complexes on this punctured neighborhood, they can be defined in terms of this J-algebra as follows. So you take kernel of the functor from representations of B opposite to Kalkin category of K, and go to, by smoothness of B, you go to perfect complexes of B tensor Kalkin, and then you go to Kalkin over B. And this kernel gives exactly the perfect complexes on the punctured neighborhood of infinity. By the way, if you look at the condensed, it's a Scholze notes just PDF file, condensed PDF, then very similar categories arise in the section about coherent duality. Now there's slightly insane statement that one can show that for when B is homotopically finite, then the functor from perfect complexes of B tensor Kalkin to representation of B opposite in Kalkin squared, which is Kalkin of Kalkin, is still a homological epimorphism onto its image. This is not an easy linear algebra, but still it holds. And the kernel of this correspond to of the corresponding extension of scalars gives exactly the internal home in dualizable categories from left modules to modules of the Kalkin categories, which in particular exist. And then there is a natural strongly continuous localization from this internal home to modules of a Kalkin category over B. And this kernel is a category of nuclear models on this neighborhood of infinity. I guess I killed everyone with this statement, but yeah, I'll stop here.
Okay, thank you. And now Q&A questions. Dima? No? Are there any questions? Actually, you promised, or at least I'm interested in the answer to the question which Maxim asked, kind of concrete realization in the case of Grassmann algebra, like 1 point.
No, I think it's too complicated.
No, I don't think it's too complicated if you just look at this directly. I mean, if you apply this general definition, it looks complicated. But I think in this case, it can be expressed in much more sensible terms.
But you cannot compute Hochschild homology yet, right? So this is the
I cannot because I mean this abstract definition it doesn't immediately allow you to compute localizing invariance.
Right.
I have another. Well, I didn't mention it, but I guess the statement which I did not completely check, but which also makes a lot of sense, that in the case of formal schemes, another way to define this nuclear models, I mean, again, unbounded version, is the following. You take this inverse system of quasi-coherent shifts on the infinitesimal neighborhoods, so you have pullbacks, and then you take the limit of this, but you take the limit in the world of dualizable categories and strongly continuous functors. And when you express explicitly what's going on, how to define this limit so that it is indeed a limit, I mean, so that it satisfies the universal property, I guess you get the same category.
well, limits, does it not?
Once again?
Continuous K-theory kind of commutative limits.
No, it doesn't. I mean, in general, it doesn't. But here, the situation is quite special. I expect, I hope that there should be a certain result that under some assumption on the inverse sequential limit, continuous K-theory will indeed commute with limits inside dualizable categories, but it doesn't hold in general.
Of course, it has to be, well, whatever, we'll discuss it. Yeah.
No, but I mean, the problem is to figure out what are the exact conditions and how to achieve this.
The limit should be just reduced to taking homology of some topological space, basically. I guess that's what's going on, right?
No, I'm not sure that you can reduce it to homology of topological space. Again, I mean, in my result, for example, on shifts on locally complex spaces, you get this homology with complex support, but here you want to get cohomology. So at least you need to do something. I mean, some additional ideas are required.
Okay. Now it's not the time to clearly. Sorry. Yeah, I mean, yeah, it's late.
Yeah.
More questions?
So I have a question related to the motivation you were saying at the beginning. If you have a complex manifold, I thought that condensed mathematics should give you some way of defining the K-theory of that as like algebraic K-theory of some maybe condensed infinity category of perfect complexes in some suitable sense. Is there anything like this, or did you say that this is not known?
Well, to be honest, I don't have a complete. I mean, I don't have an understanding on this liquid part of the theory. So, I mean, I learned it. I mean, I learned about the whole theory quite recently, and this is just a result of some partial understanding of what's going on. But I didn't look into the liquid part. So I don't have an intuition what happens there. But probably you're right. Yeah. Probably there's still some construction of dualizable category, and which might have a reasonable expression of K-theory.
Okay, thanks. But for for rigid analytic spaces, is it you said that this is possible?
For rigid analytic spaces, you can somehow reduce them to formal schemes in this framework of Raynaud.
Okay.
So I guess this is closely related.
Right, I see. Thanks.
Mm-hmm. Yeah, actually, maybe some remark about this analytic spaces. I thought about how to formalize them and for the right categories. One can live with some kind of reasonable, without any large cardinals stuff, like countably generated nuclear spaces. It will be tensor category with some countable sums and tensor product commutative with countable sums. And you don't need any more, because when consider this definition of like B tensor over A to B is equal to B, for this you need this definition of tensor product means only kind of countable inductive limit, and you don't need anything else from your tensor category.
It's confusing because kind of you do not need more than countable sets.
Yes, one can formulate to like derived Morit equivalence between analytic spaces at the end of the day, and without the actual categories.
I mean this. I mean, a lot of categories which are considered here, they are in fact what is called Aleph-1 presentable, which means
No, but Tim, we want something which has K-theory, which is uncountable. So it cannot be that small.
No, K-theory could be uncountable, of course,
No, Dima, but even for completely generated categories, K-theory can be
uncountable if considered kind of like
I mean, for
algebra
example, just a small remark that the case when it is settled that K-theory computes with limits is the special case of products. I think it's quite recent, actually, but it's known that K-theory computes with products of small DG categories.
Continuous K-theory or?
No, the usual K-theory. You take the usual product and the usual K-theory. And then what I realized actually recently, because I didn't actually understand how it works, but recently I finally understood that you can, that the products in the dualizable world, they still exist, and this result still holds. So the hope is to be able to express these sequential limits in the dualizable world, somehow to be able to reduce them either to infinite products or to some infinite semi-orthogonal decompositions, but somehow like products, not sums.
You just take the simplicial thing. I mean, you take the simplicial replacement of your diagram. This becomes some kind of simplicial set. You need a limit over that. but then you take geometric realization, and then there's an interplay between. Well, it's really a long story. I don't really want to hold people.
No, but the problem is to really prove that the inverse limit of K-theory is indeed K-theory of something.
Right.
I mean, it's not easy.
Absolutely not. Nothing is easy. For sure. But
no, something are easy to understand, but this is not.
This crucial kind of thing. It's not beautiful. But if it works, it might work. If it works, it's great.
Yeah.
Okay, more questions?
Sorry, Sasha, just to test my understanding, if you don't mind. If I want to remember your notion of nuclear modules in a sort of one sentence. So if I have a DG algebra or DG category A, I can think of modules, A-modules, as continuous functors from mod A to mod K. And what you seem to be saying is that these nuclear modules are the ones which are strongly continuous, which means the ones which also have a continuous right arch.
No. If you just take strongly continuous, you get the usual. They correspond just to the usual pseudo-perfect modules.
Wait, but you had the statement that nuclear modules are precisely this internal home from mod A to mod K in this dualizable.
No, but this internal home in this complicated category. I mean, so
yeah,
just to clarify. In general, when you take this, for example, in part 2, when you take this home dual, this is some dualizable category, but the compact objects of this category, they correspond to functors from A to T. I mean, representations of A in T.
Yeah.
But I mean, it's the compact objects. They don't generate this category. So this is dualizable.
I see. So this again, I understand now. So the point is that this way of looking at it really requires this this internal home to give you this additional structure. Thanks.
Okay, more questions?
Hi, I'm wondering if there is an analog of this construction, so not only for a punctured formal neighborhood, but for some other in scheme, like for the affine Grassmannian. Does it even make sense to talk about this as an example?
Well, it might. I think the natural question when you consider in scheme, well, in particular, I mean, countable, like countable in scheme, then the natural question is, I mean, can you describe the associated inverse limit of categories of quasi-coherent sheaves in this dualizable world? And probably this, it makes sense to consider such categories for more general in schemes than just for formal schemes. But I did not do it. I don't know actually if this how this works and if this is reasonable or not.
All right, thank you.
But just to remark that compact objects in such a limit, they will correspond to the usual perfect complexes. You know, this standard there's standard confusion that for this in schemes, the perfect complexes they don't have to be compact objects at all, but they are compact objects in this limit.
Ah, I see. Thanks.
Welcome.
More questions? Looks like everyone who wanted to ask a question has already asked it. So thank you very much. So it's a seminar record, 3 hours. So that's good. So thank you, Sasha, and thanks for those who kind of survived.
Yeah. Thank you.
All right, and this is it for today.
Okay.